This talk is going to be a little light on the theory, heavy on the applications, and it's going to build essentially on the 3-4 talks that preceded it. So essentially, we saw differential privacy, other notions of leakages for privacy and fairness. How do we put them in practice? All right, so to start, I'm going to essentially just overview zero-sum games, just two-player zero-sum games. Here you have 2 players, and player 1 goes first, makes an action. This is potentially a randomized action. And then based on the outcome of player 1, player 2 makes a randomized action. And then the utility of player 1 is the loss of player 2 and vice versa. This is kind of what makes it a zero-sum game. And you can capture this via a minimax optimization problem. So this is kind of very broad for 2 players. And it has many, many applications. You can think in economics, marketing, computer science, engineering, etc. But one application that has received a ton of attention recently in the machine learning community is generative adversarial networks. So just very briefly, what it is for maybe those of you who are not familiar with this is you have 2 boxes here. The top block is a generative model that takes in a noise seed or a noise sequence and tries to generate synthetic data, synthetic but real-looking data. And then there's a discriminator that is fed either synthetic data or real data, and it's trying to kind of figure out, is what I'm seeing synthetic or real? So this is basically a binary classifier, the one at the bottom. And they're trained via a minimax optimization framework, and they have come a long, long way. So this is somewhat outdated now. You can imagine how fast this landscape is moving. But we can generate real-looking faces that are purely synthetic. All right, so in this talk, we're going to look at 2 things. The first thing is, can we use these GANs to generate differentially private synthetic data? And this is mostly surveying work done by others. And then the other one is, can we use this minimax formulation to learn fairness schemes or decorrelation schemes that would hide a set of sensitive attributes? Okay, so let's start by the first one, which is differentially private synthetic data generation. So the question here is, why don't we use GANs as they are to publish synthetic data instead of real data? Because anyway, we're creating fake data. This synthetic data does not necessarily belong to anybody. Why not train a GAN, take the generative model, start poking it, generating synthetic data, and just publish it into the wild? It turns out this is not a good idea because these models in the training, they tend to overfit and memorize a lot of the training points that they were exposed to. So here's one example of an attack that you can do. This is part of what's known membership inference attacks, specifically for GANs. What you could do is you could imagine, for instance, if an adversary has access to the trained generative model and discriminator, and has a large data set that consists of n plus m samples. N here is the number of samples that were used in the training phase. So it has basically the samples that were used in the training phase and some extra samples, and it's trying to figure out which one of these data points belonged in the training set.
Yeah, as an ignorant, I don't really know the literature. The generator gets only noise or gets samples and noise?
So it depends on if you're doing pure synthetic data generation from scratch or if you're doing conditional generative models. So you give it some label and you ask it to generate data from that label. So for instance, I could tell my generative model, I want you to produce a digit equals 1. So it starts producing lots of different variations on the digit 1 or 2. So you can give it a label and it starts producing synthetic data according to that label. Or you could basically just give it noise and it generates data. So this is the difference between conditional generative models and pure generative models. They're trying to generate data from scratch. In this classical setting, it's essentially just a generative model that you feed it noise, and it's generating synthetic data. But the parameters of the model themselves in the training phase capture something about the training set that you've trained it on.
I guess the question is whether it's through the mitigation of that classifier that tells me real or fake, or is it actually part of the generator's input?
I'm sorry, can you repeat the question?
Can you go back one slide?
Yeah, for sure.
You see, the input to the generator is noise sequence.
Yes.
You never feed it, directly at least, an example.
Yeah.
Now, indirectly, you probably are feeding an example through the discriminator that tells it the bit of yes or no, but it's a one bit at a time.
Yeah, so in the training process, we're evaluating this loss. And this loss is on real and synthetic. And so when we do backpropagation to update the weights, that's how the generator might be overfitting to some of the training examples. That's how it might be memorizing some of the training examples. And simply, when you start using it in inference time, it might be just spitting out images that it has learned or memorized. Okay. So yeah, you can imagine there's, a suite of attacks. I'm just going to quickly go over one or two of them. This is a white box attack. What you do is you take samples that you have, and if you have access to both the trained discriminator and generator, what you do is you take each sample at a time, you feed it into the discriminator, and at the output of the discriminator, you're going to get a likelihood. What's the likelihood that the sample is real versus fake? Because it's a binary classifier, it produces likelihoods. And so what you do is you get the likelihoods over all n plus m samples, you sort them, and then you choose the top n ones. And you say, okay, I believe these are the samples that were used in the training process of this GAN. Now this is a white box attack because you need the discriminator. Now you can think of a black box type attack. Under this attack, you do not have access to the trained discriminator. So say Google has trained a GAN, and then it's using just the generative model as a machine learning as a service. So you only get to poke the GAN with some noise seed and observe something that it synthetically generates. You as a user or attacker do not have access to the trained discriminator. It turns out what you can do here is something a little bit more sophisticated. You take this trained generative model and you treat it as the ground truth, and you use it in the training of a new GAN. So you train a new generator and a new discriminator. And once you've done training, what you could do is you can use the learned discriminator to do the attack that I described on the previous slide. So we can extend the attacks we did for white box models to this black box. And people have conducted large-scale type simulations on multiple data sets. There's CFAR here, labeled faces in the wild, etc. And the foundings are a bit surprising. And in the white box case, you can essentially be accurate almost 100% on a variety of data sets. Now in the black box, the performance is significantly lower, but nonetheless, it's also quite remarkable. 40% of the time, you identify the samples that were used in the training set. So for instance, if this is a generator that was trained on patients who have cancer, and then I get a lot of data points of a lot of people, say, with or without cancer, and I can pinpoint as to which one of these patients were used in the training of the GAN, I can infer that these people are people who have cancer or something.
Are these numbers advantage over random guessing or something?
These are just
it's a binary prediction problem, right? And
no, it's 10 label, I guess.
Sorry?
CFAR 10 is 10 label.
Yeah. This is, the way you do this is, again, you have n plus m samples, and you are trying to figure out what fraction of the n samples you can correctly identify as they were used in the training of the GAN. So this is basically what fraction of these true n samples was I able to identify as samples that were used in the training.
A couple of comments. So,
sorry. So just to finish the question, I can ask you later. But the base, it's a binary class. If n and m are the same here, I could just by random guessing, I can get 50%, right?
Oh, it's not binary classification.
No. So let me try. Yes, Raf.
I think Adam is referring to the fact that you identify or not identify a person.
Sure.
So this is the binary classification.
Yes, it is.
So 37% seems compared to what, to 50%?
So okay, no, that's a very good question. So n and m, n can be much smaller than m, right?
Yeah, I guess I'm just saying those numbers, those percentages don't tell us much. If that's advantage over the natural baseline, then that's fine. But if those are actual accuracy, classification.
No, that's a very good question. I have to check back the paper. This is not my own work, but I think they're not doing relative gain. They're just doing what fraction of these points was I able to.
Okay, and then I guess to decide how impressed we are, we probably need to know like N over M or something. But maybe it's not so important.
Sure. You need to know N over M. You're right.
So one comment is that any kind of model, especially this sort of deep generative model, it's going to always overfit a little bit, right? So instead of absolute ranks, probably some sort of confidence things are perhaps more interesting. And then the second comment is that like there are a lot of overfitting tests for GANs, right? All this inception score and such like that. And they all show that GANs overfit. They basically just generate stuff from the training. Right? So I was just wondering how those results can be reconciled with what you're seeing.
Yeah, I'm just giving one example from one paper to show that if you use this method, it's a bad idea. That's it. So this is neither my result nor am I saying this is the only one that shows this problem. Yeah. All right. So one potential fix here is to try to go to differential privacy as a way to escape this problem. And this, I think, in my own opinion, is a good strategy for this problem. So here, I'm sure there's a ton of experts on differential privacy, but just in case you're not, what happens is you're training a machine learning model in this specific context. It's much broader than just training machine learning models. And the idea is if you train the model on a certain data set that you've acquired versus training it on a data set that includes everybody except, say, for Bob, you want these two things to be statistically very similar. And the kind of rigorous formula for the statistical similarity is the one that I'm showing here. And it's saying that the distributions of M on D and D prime in neighboring data set should be multiplicatively closed. And there's this epsilon that describes the multiplicative closeness, and then additively also closed. And delta is the parameter that describes that. And just for the sake of completeness, we think of delta as something 1 over a polynomial in the size of the set that we're using in the training process, and we think of epsilon as something like single digit. There's absolutely no agreement on these things, but these are just a rule of thumb. Okay, so think of delta in practice as 10 to the negative 6 or 10 to the negative 7 for practical data set sizes, and epsilon anywhere between, let's say, 1 and 10 or something like that. All right, so to train machine learning models with differential privacy, there's been many, many attempts. I work at Google now, so let me try to advertise for our recent attempt. So we've recently open sourced what's known as TensorFlow Privacy, and what it allows is for people who are experts on machine learning, not necessarily experts on privacy, especially differential privacy, to train machine learning models with differential privacy. So all you have to add is just a few lines of code in order to use this package. It's a Python package, integrates very well with TensorFlow, and you're suddenly in the business of training your model with differential privacy. Now I have to say there's a caveat here, which is we do not guarantee that the performance is going to be preserved. You might have to auto-tune a lot of things to find the right architecture, the right parameters, epsilon and delta, etc. So, but this is doing the right thing, and then how you choose to use it or whether or not you want to use it is a separate question. Okay, so let's see how we might use differential privacy for this problem. One way of doing it is to say, in the training process of the GAN, what I'm going to do is I'm going to inject the process, inject noise into the process of training the discriminator. This is a classical, let's say, binary classifier. And in its training, let's say I'm using stochastic gradient descent, I'll introduce some noise. And then rely on the post-processing property of differential privacy to ensure that the generator is itself differentially private. Because the generator only gets gradients backpropagated from the discriminator. It never touches the real data directly.
So just to make sure I understand this correctly, so you're saying we only add noise at basically at the deep, like that, I guess, more shallow layers, because that is taken back via backpropagation.
Yeah, so I'm trying to stay at a high level in this talk. This is an excellent question. The idea here is the following. The discriminator itself is going to see either fake data, which we don't care about, or real data, real samples, right? And so you can think of this as a query computed on real samples. So if I can ensure that this thing here is differentially private, this is a differentially private query, then I'm safe, because anything else I do is going to be some post-processing on this differentially private query. That's essentially how we're doing it. So post-processing differentially private queries is differentially private. Okay. This is not the only way of doing it. You can think of other better ways. This is just one way of doing it in this specific work. Okay, so just to be a bit more precise, here we're training a Wasserstein GAN, and the only difference you can spot is this line here, where we're doing the stochastic gradient descent update step. We're adding Gaussian noise. It turns out that adding Gaussian noise of a certain type, without going into too much of the details, does the job here for this specific model, a Wasserstein GAN. Okay. Now let's look at the results. The leftmost plot here from my side is no differential privacy. I think delta was chosen to be 10 to the negative 5 for this specific simulation, and we're varying epsilon here. And as you can see, when epsilon is 29, we get good produced digits. We're taking the k nearest neighbors in the underlying data set to just see kind of what is the most similar data points to what we've generated. But once we hit the single digit regime, things start getting bad. Now, I'm giving this example just to highlight that this is a challenging setting for differential privacy. This is not to say we cannot do it. This is just to say that there's more work that needs to be put in this direction. And I'm sure that perhaps a lot of you are aware that differentially private synthetic data is very important for companies and also government institutions and others. There's even competitions. I heard there's been some discussions here on this problem. One way is to take this approach, find the right architectures, find the right implementations. Hopefully TensorFlow is going to ease this process for many of the DP experts in this community. And another way is to understand the structure of the application. For instance, if we're generating location traces, you can do better by understanding kind of the right context of the application. Okay? All right. So now let's move to the second part of the talk, which is how do we create representations that decorrelate data from a set of sensitive attributes. Now in this setting, this is very close to what Lalita, Flavio, and Aaron talked about earlier today. We have a data set, and there's some sensitive attribute. For instance, here, rich versus poor. It could be gender, it could be race, it could be faith, sexual orientation, so on and so forth. And what we're doing is we're trying to design a mechanism that produces a representation of the data that hopefully decorrelates that representation from the sensitive attributes. So we're designing decorrelators, essentially. Okay? Now, you can do it in many different ways. Today, we talked about various ways of measuring leakages. And I'm going to use the simplest of all. This is kind of the most naive approach, which is I'm going to measure leakage between the representation and the sensitive attribute using mutual information. This is by no way the best way of measuring leakage. This is just the simplest way. Now, there's an issue here. If we want to design this mechanism using this leakage notion, we have to have access to the distribution. If I don't know the joint distribution between the data and the sensitive attributes, I cannot quantify mutual information and hence design the decorrelator. And you could perhaps pitch taking an empirical risk minimization approach with mutual information kind of as the quantity we're trying to optimize. People have done this, but it's challenging. So we know how to do it with things like L2 loss and perhaps with log loss, etc. But with mutual information, it's somewhat challenging. So just to give you an idea, in the literature, there's people that do lower and upper bounds on this quantity, and then instead of optimizing mutual information itself or some estimate of it, they optimize a tight lower or upper bound. So if you're trying to do max mutual information, you would maximize a lower bound instead. If you're trying to do minimize mutual information, you minimize an upper bound on it. So they take these methods that are called variational approaches. Okay, so it's not tricky. It's very tricky. It's not that easy. And so we have our own take on how we fix this issue. We're going to kind of expand the problem a bit, and then we can fold it back. And so we're going to view it as, again, a game between two players. The first player here is this decorrelator. and the second player is some attacker. The task of the decorrelator is to create the representation x hat that hopefully decorrelates x hat from S. And then the attacker tries to look at this representation and guesses the sensitive attributes. It produces S hat. I can produce either an estimate of S directly, or I can produce some likelihood on it, some belief on it. Okay? So now from the adversary's perspective, we're going to measure the adversary's loss as the expected value of some little loss L, I'll talk about this in a minute, between S hat and S. Okay, so H of G is nothing but S hat, what you produce as an estimate of S. And because we're doing a minimax zero-sum game, we're going to formulate the problem as a minimax one. So the adversary's loss is the decorrelator's gain. So what we're trying to solve here is a minimax problem over the negative of the loss subject to a constraint. Now this constraint is important. If I don't put this constraint, what I can do is I can simply just generate independent data here, and I can perfectly fool the attacker. The attacker wouldn't be able to guess the sensitive attribute reliably.
Yes, I have one question to clarify. The privatizer gets both the sensitive attribute and the data X.
So in the most general setting, yes, but you can think of ways of designing this without having access to either one. Yeah. So now this constraint is important because I want the representations of the data to be as close as possible to the true thing. So I'm measuring some distortion between G computed on XS, which is X hat, and the true X. And I'm trying to make sure that the expected distortion is below some threshold. Now this distance function here can be anything. I'm mostly going to use L2. But if you, for instance, want to use these representations for a classification task, you can choose this distance function to be the performance of a classifier trained on these representations. But for this talk, I'm just going to use L2 distances and something called structured similarity index. I'll get to it in a bit. All right, so now you might like this or not, but I think there are two fundamental questions here. The first one is, why do we need yet another formulation for this kind of problem of decorrelating data from sensitive attributes? Why are we looking at something even more complex, minimax game? And how does this really kind of gives us a way out from the issue of not having access to joint distributions? Because in what I've just defined, I'm still using expectations over distributions. So there's still that issue. Now, to tackle the first question, it turns out that depending on how I choose this little loss function, I can do something like squared loss, or I can do 0-1 loss or log loss, etc. I can even use the alpha losses that Lalita talked about earlier today. We kind of recover an array of attacks and adversarial models that are extensively studied in the information theory and statistics communities. Okay, let me just try to be a bit more precise about one that I'm going to use in this talk, which is this row, the log loss. So let's say I take the formulation that I had, and here, instead of this little l, I'm going to use the log loss. Okay? If I use this log loss, then we can show that this minimax problem essentially is equivalent to minimizing the mutual information between x hat and s subject to a distortion constraint. So in this case, this max here has a closed form solution. What the adversary is doing is essentially computing the posterior, and that's the optimal adversarial strategy. You can plug it in and reduce the problem to a simple minimization problem. Now you might say, okay, I'm back to optimizing mutual information, so how did this help me in practice? And I'll show you how it's going to help you. We're not going to solve this problem. We're going to solve the other one, with in mind that they're actually equivalent. Okay? So here's how we're going to do it. We're going to replace these two boxes with a generative model. This is a neural network with finite capacity with some parameters theta p. And the adversary with, again, a classifier, a feedforward neural network with, again, a finite capacity and parameters theta a. And instead of solving the problem on the population risk, we're going to formulate an empirical loss. Let's say here little l is just log loss. This is the classical cross-entropy loss that's commonly used in machine learning. And I'm going to define a data-driven version of the problem here. So I'm going to do minimax over the parameters of the generator and the attacker of an empirical loss, and then subject to this empirical distortion constraint. Now, this is easy to be done because I'm only using cross-entropy loss. I'm not using anything information theoretic in some sense for the empirical loss. I'm not using mutual informations or KL distances, or things that would require upper and lower bounds. Okay? But there's one challenge here, which is this constraint. Now, you could, for instance, take the constraint and plug it into the main objective function via a Lagrange multiplier and just optimize the Lagrangian. But that wouldn't always lead to a good result because this thing is not necessarily a convex problem. So let me try to be a bit more precise about how we did it. So the way we did it is we used something called the penalty method, which is a really old method, which instead of using one Lagrange multiplier here, it solves a sequence of optimization problems. And it starts with a small penalty and increases the penalty as the training proceeds. What it's saying is if you're off, you need to penalize things more. So you repeatedly solve the problem with increasing kind of multipliers. This is representing the penalty. And that actually ended up working well in practice. There are no kind of rigorous guarantees on the performance of this method, but in practice, it actually worked well. So let me show you some results. Let's take this simple data set. This is called the GENKI data set. It's a data set of face images. It's a small data set, about 2,000 images, grayscale images, small images, 16 by 16. The way we train things here is by treating gender as the sensitive attribute. And after we are done training and we learn the representations, we're going to try to see if we can use the representations in order to learn facial expression directly from the representations. Okay? So just some cool diagrams showing the architecture of what we used. For the adversary, we're using just a 4-layer neural network. It's a small neural network because the data set is simple. So there's 2 convolutional neural net layers and 2 fully connected layers here. But for the generative model, we have 2 different ways of doing it. So one way is to take these 16 by 16 images and to form a 256-dimensional vector, just to unwrap it, and then pad a noise sequence here of basically Gaussian noise of 100 dimensions. So now you end up having a 356-dimensional vector, and you use some type of autoencoder architecture. So you compress down the data, and then you go up. You can see that what's happening here is we're mixing the data with the noise in a nonlinear fashion using this neural network. And then you can reshape at the output to get an image, a 16 by 16 image. This is one way of doing things, and this is going to be the better way of doing things. But this is not scalable because for large images, we need a larger noise sequence, and then things basically are going to lead to huge computational cost. Another way of doing things is to say, all right, I'm going to take the noise sequence here, the 100-dimensional noise vector, and I'm going to shape it up using the convolutional operations into a kind of a 256-dimensional vector, which I can reshape to make it look like an image, 16 by 16 image. And then I'm going to take this noise image and add it to my data. And that's how I get the privatized version of my data. So these are 2 different architectures. You can construct many other architectures. These are just 2 simple ones we played with. All right, so let me try to show you here the results. I just want you to focus on this one. What I'm plotting is the expression classification. So from these kind of representations, how well can I guess the facial expression of the person versus the gender classification? How well can I guess the sensitive attribute? So we want this to be very close to 0.5 because we have 2 genders. So we want it to be kind of a flip of a coin. Anything that is very close to 0.5 is great. And we want this to be as good as possible because we want to preserve the expression classification task. Even though we have not used expression classification in the training, the way I formulated the problem does not need that task. As you can see, this blue curve represents the first architecture I showed you, does a quite good job. I mean, at a performance of about 0.81 or 0.82 or something, I get almost perfect, fooling of the attacker. This is a finite capacity attacker again, so we're not fooling any attacker out there. And the other architecture is doing reasonably well, but it's a little worse. Now, I'm comparing this to methods that would just take the data and add noise directly to the data. I could add Laplace noise, or I could add Gaussian noise to the data, and then see what I get in terms of gender classification or expression classification, and that's not a kind of a good strategy for this specific problem. Okay? And what I could do is, after I create these representations, I can go ahead and estimate the mutual information between the representations and the sensitive attributes. And this is just to show that mutual information is dropping as I increase the distortion budget that I have.
And what distortion metric are you using here?
Just L2. So you take two images, you take their difference, and you sum squared over all the pixels of the image.
Did the images,
for this one.
Did it get blurry?
Yeah, I'm going to show you. This is a great question. So here's I'm going to show you. Let's focus on this side here. So I've split them into males versus females. This is the original kind of set of images, and then you have the kind of filtered ones. And you can see, at least on the ones that we misclassified, so this is success for us, you can see that what we're learning is essentially for males to hide the mustache. You can see here, for instance, some of the mustache or geometry of the chin and others. Facial hair is also evident in some of these ones. And for women, it's probably going to be lipstick and such. So this is just basically as a sanity check. Now, this is great. Let's talk about cases where this sensitive attribute is large. In the previous example, it was just binary, male versus female. So what do we do if now we have basically many classes? Training a GAN with 1,000 classes or 2,000 classes is basically not feasible. It's computationally very, very expensive. So there's a nice trick to overcome this limitation of our model. What we're going to do is, again, we're going to use a filter to edit the data. And then we're going to compare the data to a reference point. And then our discriminator in this case, we're calling it the Siamese discriminator. I'll explain in a bit what it is. It's just going to compare these two things and give you a similarity metric between them. So let me be a bit more specific. So let's consider this architecture. I feed images, I compress them down, and then I add noise here. And then I reconstruct the images. So I get kind of here the noisy images. And I have reference images. I'm going to use the same two neural networks. These are essentially extracting features. And I'm going to take a distance similarity between these two features. And I'm going to say, OK, these two images are coming from, let's say, the same person, or a person with the same attribute. So there's a distance similarity here that's used to compare the output of these two neural networks. These are the same two neural networks that are extracting the same embeddings on their input. Okay? So we've tried it with IDs on syllab A, the data set. This is by no way a cherry-picked block, because you can see in some cases it's great, in some cases it's terrible. If we have high distortion, I forgot the exact value of the distortion we used here, you can see that what it's happening is it's, in this case, preserving to a certain extent the gender, but in many cases in this row, you cannot tell the identity of the person. You cannot map the privatized image to the identity of the person. There's enough distortion introduced, but you can still say there's a face of somebody. Sometimes you can still even tell the gender, but the identity in some sense is to a certain extent hidden. There's misses and hits here. But then if you do low distortion, things tend to be pretty well preserved. You're not essentially distorting the image by much. At the same time, you're not hiding the ID of the person by much. And for this, we didn't use the L2 distortion. We used what's known as structured similarity index. This is a notion of similarity between images that is used in computer vision. Turns out it's much better than L2. All right, yet another example. This is the last one. This is the human activity recognition data set. It's essentially a time series, 561-dimensional time series of sensory data in the frequency and time domain. And here you have people who are walking, either walking upstairs, walking downstairs, sitting, laying down, etc. And again, what you want to do is hide their identity, but you want to allow people to learn this activity reliably. Okay, again, I mean, essentially more or less the same results. We can show that as you increase the distortion budget, you can fool the attacker. In this case, because we have, I think, 5 people in the or 8 people, we get down to a small accuracy. All right, so with this, I'm going to stop here and then take any questions you may have. Thanks.
This is a comment I think it might be interesting to see, because there are some existing tests of overfitting with GANs, right? So what might be interesting to see is if some of your private GANs or these kinds of GANs, if they can get around those tests.
That's a great point. Yeah. So what you're saying is train a differentially private GAN and then run all these metrics and tests and see.
What's happening.
Yeah.
Right, because those tests always
Yeah, have you guys tested with artificial data? I'm just wondering, like, if you have a case where you know the distribution, you can actually solve that optimization exactly.
We did. In fact, I mean, I had slides on this with Gaussian data, and in this case, as you're saying, we know the theoretic optimum of the minimax game, and we tried to do a data-driven approach. And in fact, what these plots are showing for 8-dimensional Gaussian mixture models, that what we're doing in practice matches exactly the optimum game theoretic, what you would expect, you know, the problem to.
For a binary something.
And just to clarify one thing, like, and when you mention about the adversary's accuracy, this is a new adversary that you train on the. It's not the adversary in the GAN. You go and train a new model, train for that, or
that's a very good point. So this is an interesting setting because we're assuming there's a data holder that has the entire data set and wants to potentially release representations that have been decorrelated from the sensitive attribute, right? So here, the metric of interest is the loss on the training set, the empirical loss that you get on the training set. Now, what you could do is you could, after you're done training, you could go back and go through your data set, for instance, measure the loss on each one of them, and you could say, wait a second, the loss here is actually, the attacker's loss is very small, so I'm not going to release the sample. Whereas here, the loss is sufficiently high, I'm going to release these samples. So even though in the training phase, we've used the empirical loss on the entire training set, but what you decide to release or not is up to you. You could measure the loss on a sample basis and then choose to release it or not. And you would notice, for instance, here that the loss is low, whereas there the loss is high.